Today I wanted to talk to you about timber structures and SAFIR, of course, through two of the many timber projects we had over the past few years. The first one revolves around the timber concrete warehouses, which we call the Codifab project, where we had to study the chronological collapse of timber concrete structures and the real fire scenarios. And the second topic I wanted to talk to you about is the Paris 2024 Aquatic Center, which you may have heard of, and how we assess the fire stability of the glow laminated timber upper structure. So, okay, the SAFIR users faced many challenges when dealing with timber structures. The first challenge we face, of course, is the thermal properties of timber with the thermal conductivity, specific heat, density, moisture content. There's also chairing that appears at a different temperature. We also have different properties evolution with the temperature in the scientific papers. So, okay, but let's say that these properties are well known, or they are imposed by design codes or regulations. We still have to face the mechanical properties challenge of timber with the compressive, tensile, and bending stress. We also have to input FC and FT in SAFIR, so it can be quite a bit challenging. We'll see that torsion also had a great influence on the results. And here also you have different evolutions of those properties with the temperature. But okay, let's say that this part is also imposed by regulation codes or design codes. You still have to face the main challenges, that is the structural modeling in itself, with the boundary conditions, the connections. You have to take into account instabilities like buckling, like lateral buckling, torsional buckling. So it is complicated enough at cold temperature, but at high temperature it gets even worse. So then you have to also face the fact that the structural timber elements are part of the heat load, so that can be quite challenging. And also, what about the cooling phase? What about the mechanical properties of timber? When do we stop our simulations? So everything here is quite challenging with timber. And today I won't answer to all these questions, of course, but I hope my presentation will raise some questions, and maybe it will give you some ideas on how to model timber with SAFIR. So the first topic I wanted to talk to you about today is the Codifab project. But before diving into it, let's take simply supported GLT beam, 12-meter span, which is laterally and torsionally restrained at mid span, which is exposed with the ISO fire curve. You can calculate its fire resistance in bending, of course, and in bending plus lateral buckling. So we'll first do it with thanks to the Eurocode 5, which is the design code in France. So the fire resistance is given when the continuous line crosses the dashed line here. So we see that we have a fire resistance of 60 minutes and around 30 minutes here. So we have a time difference of, let's say, 30 minutes between those two values. So now what you can do is you can perform a thermal transfer analysis with the SAFIR, and we can compute manually the reduced cross section and do this exact same calculation. Here you can see that the values are a bit shifted on the left side, and we lose, let's say, 10 minutes for the fire resistance. Now that you have done your thermal transfer analysis, what you can do is you can perform a thermomechanical analysis on SAFIR. So, of course, in pure bending, you will get the exact same results, which is normal. But what's interesting here is that you only lose 5 minutes if you take into account the lateral buckling in your simulations. So it's quite a big difference between what we lose thanks to the Eurocode 5. So what we did here is we updated the torsional properties at the time of failure, thanks to the use of insulation materials in the torsion calculations. And here what we can see is, okay, the values are not exactly the same, but are more in line with what the Eurocode 5 says. So, okay, torsion played an important role here on the fire resistance, and that's what we had to study in the Codifab study. So, for a bit of a context, that was a study that was following the 2020 release of the Codifab guidelines on timber concrete warehouses. Indeed, it's a huge challenge for the wood industry in France because the fire brigade and the authorities are a bit severe on the fire requirements, and they are a bit reluctant to having such timber concrete structures. On the more technical part, we had to deal with the typical timber concrete warehouse that was designed for fire resistance of 15 minutes. For the objectives, of course, we had to get the fire resistance on the real fire scenarios, and we had to go far enough in the progressive collapse because we wanted to model everything in 3D. So it can be quite challenging with wood and with the SAFIR. When one element fails, the calculation stops, so it can be complicated. And for the challenges, of course, it was to get the right collapse time and to create an iterative process in order to update the torsion, as I mentioned earlier. So here you have the SAFIR model with some of the assumptions, like we had fixed reinforced concrete columns. Almost all connections were pinned. We studied 2 fire start positions on the different load combinations like snow, wind, etc. Well, we'll talk a bit about it later, but we needed to update the torsional properties to take into account what I said earlier. And what we did also for the connections is we took into account the eccentricity that is generated when one solid fails and the other stays in place, which generates torsion into the main beams. Here you have some diamond visualizations of the cross section. So you can see on the left side that we had to deal with the timber variable inertia beams, 20-meter span. And on the right side, you have the reinforced columns and the cross-sectional views on diamond. Here you have some of the max temperature that is seen by the structural elements. You can see that around 15 minutes, the flashover happens and almost everything is impacted by very high temperatures. But okay, now let's dive a bit into our iterative process and how we dealt with the torsional update. So, okay, you start from your first model of SAFIR. You run SAFIR from time t0, and you get a collapse time of let's say 30 minutes. So it's your first iteration. So I need to update the torsional properties at 30 minutes, and I relaunch back SAFIR from scratch. So now I get another collapse time of, let's say, this time 20 minutes. So it's not my first iteration anymore. And I have to ask myself, is the time at which I calculated the torsional properties coherent with the collapse time? So here, remember, I calculated the torsional properties at 30 minutes. So here the convergence criteria is not met. So I need to update again the torsional properties, this time at 20 minutes. And I do this again and again and again until I finally reach a time step or an iteration where I get a collapse time of 25 minutes, where I calculated the torsional properties at 25 minutes. So the convergence criteria is met. And I can say, okay, SAFIR can give me the right collapsed element. I can remove those elements from the calculation. I can launch back SAFIR with that the displacement history of that last iteration. So what I will do, I will spare you all these iterations, but I will just show the main results here. So we can clearly see that we removed all the GLT purlins from the SAFIR model. That's around, let's say, 60 minutes. We are left with only the main beams, the main timber beams. So that was quite interesting. And also what's interesting, of course, to look at the bending moment evolutions in the main beams. So we can clearly see that from the beginning to the end, the bending moments are well reduced, and that because of the structures are only loaded anymore by their self-weight. So that was quite interesting. And this led, of course, to design optimizations, and the Codifab guidelines were updated thanks to those calculations. So it was a great project. The second topic I wanted to talk to you about today is the aquatic center. This is a structure that was created for the 2024 Olympic Games here in France. Of course, we had the fire requirements, fire resistance of the structure of 30 to 60 minutes. We also had to demonstrate that if one element of the roof were to collapse, this would not lead to the collapse of the whole structure. We also had two fire development, I would say, requirements. The first one was we wanted to be sure that there was no spread of the fire to the whole timber structures, and also that the timber component did not maintain the fire indefinitely. So, because you can easily understand that if the fire is maintained indefinitely and is spread to the whole structure, eventually the structure will fail. So here you have the 3D views of the structure, a structure that is 100 meter by 110 meter. You have here in red the main columns that are in GLT. They are linked together by catenary beams, tensile beams that are also in GLT. You also have steel tension bars here at every column that gives equilibrium to the system. And you have also other wooden and steel elements like the cross bracing, the roof bracings, and the bracing beams here. So for the fire resistance, we decided to study three main scenarios. These were discussed with the authorities. So the first one we studied was the fire in the refreshment zone. You know, when you take your beer at halftime of a match. So for this scenario, it was impacting mainly the columns, the timber columns. And we had some issues at first on the first iteration when the fire was maintained indefinitely here on top of the columns, just under the stands and the concrete stand. So we had to protect those elements in order to carry out our SAFIR simulations after. The second scenario was fire at the spotlights just under the roof. That was mainly impacting, of course, the catenary beams. Here also we had some issues at the first iteration because the fire was spread to the whole roof, whole timber roof. So we had also here to protect some of the spotlights here, and in order to reduce the heat load and to perform our thermomechanical analysis after with the SAFIR. And finally, the last scenario was the fire at the screens. That was also impacting mainly the catenary beams. So the first scenario we studied was the main athlete's big screen, which you can see here in orange in the center of the pool. And the second one was the rowboat smaller screen that you can see here on the orange here in the other side of the pool. For this simulation, we carried out real fire tests in order to get data and to implement it in our CFD simulations. So that was quite interesting also. And okay, back to the SAFIR modeling here. Here I summed up the position of the fire scenarios. And of course, we had the whole geometry here. We couldn't afford to model it everything in 3D. So what we decided to do is to create three partial 3D models on the SAFIR. So one for the eastern part with the fire of the small screens, the center one for the spotlight fire and the refreshment zone fire, and the west one for the biggest screen, and that's it. The geometry was provided to us by our customer. So with such complex structures, sometimes the elements are not linked exactly together. So what we had to do is to we used an extensive amount of the same commands in order to link those elements. We also had to use an extensive amount of the relax command on the SAFIR because we wanted to take into account the stiffness of the connections. We also carried out a sensitivity analysis on those stiffness connections. So that was a bit challenging also here. And here, well, you have some visualizations of the snow load or the wind load that were taken into account thanks to the trap lock beam command in SAFIR. Here, I wanted just to resume the fire scenarios. on the most impacted zone by the fire for each scenarios. So on the east model, we had the small screens that were impacting mainly the steel facade and the catenary beams here. On the middle model, we had the fire in the refreshment zone, which was impacting mainly the columns and the wooden hole here, here. And the spotlight fire and the big screen were impacting mainly the catenary beams here and here. So here I wanted to show you the diamond visualization of the deform shape and the displacement field, or an example of two of the scenarios on which we carried out simulation. So I present the results after 4 hours of fire. So you may ask, why after 4 hours? When the fire scenarios are only lasting around 30 to 60 minutes. So here I plotted the compressive stress and the tensile stress resistance evolution of the main timber elements that was computed exactly in the same way we did with the Codifab project. And you can clearly see that the resistance keeps decreasing well after the fire had stopped. So if you were to only calculate and run your SAFIR simulations for the fire scenario duration, this would lead to unsafe results. And here with this blue curve here, we try to find the time at which we get an horizontal asymptote, just to see that, okay, here it happens at, let's say, 240 minutes, so 4 hours of fires, and after that, we can expect that nothing more will happen. So our simulations are on the safe side, but not too much. So that was it for me. Of course, this led to design optimizations, and the authorities were reassured, and we had a great event this summer. For the conclusions, on the first part, we saw that, of course, torsion played an important role on SAFIR. We also demonstrated that it was possible to achieve progressive collapse on SAFIR thanks to the iterative process as we implemented in SAFIR. This led, of course, to design optimizations and confirmations for the timber industry in France. On the second topic, we assessed the fire resistance thanks to real fire scenarios, and thanks to SAFIR, this led, of course, to design optimizations also. And on the perspective, a bit more for Thomas and Jean-Marc for SAFIR, it would be interesting to have a SAFIR explicit solver, because when dealing with such complex 3D structures, when one element fails, it is a bit complicated to see what happens after. It could be also interesting to have the torsional properties updated in SAFIR code with the temperature evolution. It will also be interesting to have a mechanical restart on SAFIR, because it would spare an extensive amount of time when we have to do iterative process like the one in the Codifab project. And of course, there are more and more complex timber projects that are done with SAFIR, and that's great. Warehouses, office buildings, car parks, arenas, gymnasiums. So that's always interesting. And I showed a bit of the new capabilities of Diamond here. And I think new features are needed, because other thermomechanical software can do other things. So why not SAFIR and Diamond? Of course, there's still many research to be done for the fire structural timber design, including connections, which is an important topic. And of course, experimental data is always needed, because when dealing with such complex structures, it's important to have that data and to implement it in our simulation. Just before the question, I wanted to thank those three guys, so Mr. Xavier Duponchel and Mr. Mathieu Denis for the Codifab project and for the Aquatic Center project. they got me involved into such a challenging project, so thanks to them. And also, I wanted to thank Mr. Guillaume, which is the developer of SAFIR here at Efectis, which is also working on the update of Diamond in its 2024 or 2025 version, without whom it wouldn't have been possible to have such a great presentation today. So if you have any question, I will be pleased to answer them, if I can at least.